I am here today to present an overview of my doctoral dissertation to you. In this presentation, I'll give a brief introduction of what the topic is about and explain what additive manufacturing is, the motives and aims of the study objectives, the guiding research questions, methodology study plan used, the main results and contributions from scientific aspect and industrial aspect. Then I'll give a conclusion and suggestions or recommendations for further studies. So in an introduction or background to the study, we are all aware, or some of us are already aware of the reasons why, or we've seen that in our apartment we are asked to sort trash. Have you ever wondered that is it just that they want to collect material, or what is the motive? There is what we call sustainability or circular economy. And this is such that we want to preserve the earth. The resources are getting scarce, resources are finishing, and because of that, we need to protect the environment. Manufacturing industries or industrial companies use large sums of materials, and in so doing, they are polluting the earth. There is what we call global warming, if maybe we have heard already. It is the tapping of the heat escaping the earth into the atmosphere by some gases. And one gas which is very common or main contributor is the carbon dioxide. And if you look at this graph, we will see that manufacturing or different manufacturing methods contribute to this differently. Then what is additive manufacturing? So my main thesis is about additive manufacturing. We might have heard about 3D printing. 3D printing and additive manufacturing are the same. Additive manufacturing, we will say, is the engineering normal terms, and 3D will be the common name for it. So additive manufacturing can be defined by the definition as a process of joining materials to make parts from 3D model data. Usually, when we say 3D model, it's about computer information, layer by layer, as opposed to subtractive manufacturing, where you are actually having a big block and you're cutting away. Or then formative manufacturing methodologies, you have a liquid and then you put in some mold and it forms it. So additive manufacturing is building the components layer by layer, and the stepwise approach to additive manufacturing is what this image shows. So first you should have the idea, then you convert it into a format that is readable by the machine. First of all, you have to slice it into some layers and then the readable version. Then you go to the machine to make the setup. You build it layer by layer. You remove the parts, you clean, so we call it the post-processing. And then you do the quality assurance and then also the application. So that is the steps to additive manufacturing. So additive manufacturing, we know, is growing year by year. Though, if you look at this graph, we will see that the share of application is almost the same, but in value-wise, it is really increasing. And here are some of the common users of additive manufacturing. So additive manufacturing, according to the standard, I already made the explanation from ISO standard, there are 7 subcategories of additive manufacturing, such as powder bed fusion, directed energy deposition. And out of these, about 5, as shown in the orange region, are applicable to metal-based materials. So AM can, if I say AM, it's referring to additive manufacturing. It is, these 5 can make metal-based components. Plastics and other materials can also be made with all the other, including these 5 methodologies. Then when we come to the powder bed fusion, which is coming to then what I have done, it's about, we have 2 electron beam based, so the energy source is an electron beam based, And then we have the laser powder bed fusion, or laser beam based. I will shorten it as LPBF. And that is the main field what I have done my studies. So this is a schematic presentation of what laser powder bed fusion is. I will not go through this, just a graphical view of it. And then now somebody may ask, what was my reason for choosing this topic or choosing laser powder bed fusion? So laser powder bed fusion is a manufacturing method that is helping industries to create really interesting, impossible geometries which were not possible to get by previous or conventional, traditional methods. Also about the sustainability aspects is that additive manufacturing is a growing technology, but if you look at the literature, there aren't really studies relating to the environmental, the economic, and the social aspects. And for this current world where we live in now, everything is talking about sustainability. So I saw the gap in literature, and I thought that I would try my best to fill in the gap, and this is what led to the study currently. So I applied a life cycle thinking to this study because most of the studies I had seen were only concentrating on the production. But I was wondering what would be the overall benefit of the process to the society or to the industry. Again, also on the motivation, it was about the business models to look at how companies can adapt AM in a way that will be beneficial also to their operations as they also think about the sustainability and the circular economy. So the circular economy is that when we take something, it goes back into the system, or we prolong the lifespan of the component. And maybe we know digitalization. We all know that these days everything we do is being digitalized. Even to go to the offices, you don't find them, you go to the computer. So it's the new trend, and it's helping industries to find new ways to do things. The thesis was guided by 3 main objectives. So investigate and perform experimental studies on the sustainability aspects, and also to create a basic model of life cycle cost, how companies or how additive manufacturing affects life cycle cost, and also to modify the design based on industrial objective or industrial review. And the research questions guiding this thesis were 3 also. So how can the factors which are affecting the sustainability be experimentally measured? And also how does life cycle cost driven simulation, life cycle cost driven DFAM is designed for additive manufacturing, which means you are making the components in relation to satisfy some rules you should be able to fulfill to get a good part printed. And then to also have an overall overview with industrial representatives about the model to discuss it. And there were 5 publications out of this study. So the main results were, as I said, publication 1 was about the life cycle supply chain, life cycle assessment studies, where I would measure the input material and then the output component plus the emissions or the waste that were created with it. Then to answer to research question 2, there was the simulation driven for additive manufacturing and life cycle cost studies. And then also the suitability of this model was in the publication 5. And then the final part, which was the summary of the thesis, was interaction with business or industrial representatives to analyze how this tool, the life cycle driven DFAM model, could help them to achieve the necessary benefits in terms of economics and also the environment. So this is still about what I have already mentioned. Okay. So the main scientific contribution were the 5 publications, and also the identified ways or resources and cost efficacy can be achieved. And some of these things were the product design. It was identified that the product design, which includes the processing, the manufacturing process, and the materials, and also the process parameters, which we are selecting from the machines, such as the laser power or the scanning speed. All of these have an effect on the process. One thing also I have to say is that additive manufacturing, or the laser powder bed fusion, is being criticized for the high energy usage. And so on the manufacturing phase, when you're able to optimize these affecting factors, we are able to reduce the energy consumptions. And also the material usage of the process was something that was quite impressive, because it also affects the sustainability, as you can actually build from the exact amount of material you need without creating waste or excess powder. And let me also say that powder bed fusion is based on metallic powder, so we don't have a block of metal, but just a powder which we are laying layer by layer. So here are some of the identified things that you could use to enhance the resource efficiency and cost efficacy. So then simulation-driven design was using computer-based tools to plan your design. Based on DFAM, as I said, design for additive manufacturing. Here is an example of design optimization, what we call lattices. So you create the components so that it takes up, instead of having a solid body in the air, you create holes inside them intentionally to reduce weight and also to enhance the functionality. Here is another optimization, what we call topology optimization. So you're also creating intentional holes to enhance the functionality and also to reduce the volume of the components. Then here comes the main contribution, which was derived for the industry. It's called the life cycle cost-driven DFAM model or tool. So here it is talking about first the design. So we have the design system, where we are talking about the computer programming and designing the model, and also the production phase. These aspects affect a lot, and when you should be able to consider all these green areas of the box. Then when it comes to the use phase, once you have an optimized component, we are assured that we are going to get, or additive manufacturing assures of better functioning components. An example, if it's an application for dynamic, which means the flying aeroplane or something, we are going to reduce energy, because the heavier the component, the more fuel you are consuming, the lighter, the less fuel, and then you reduce the carbon dioxide. And that is one functionality or benefit of additive manufacturing, for instance, to the aerospace. Then when we have finished using the parts, we are sure we can reuse it or repair it for another reuse, because the component is designed such that it is reusable, it is thought into it, and it can also be remanufactured for another use. But then there is something industrial companies were hinted to, and that is the hidden cost. So it's not just about the process. Something like post-processing, if not well planned, can actually bring some surprises to the companies. And this model was able to identify that and point it out to industrial users. So the whole interest of additive manufacturing is not just the production. The industrial companies shouldn't adopt to it looking at only the production, but they should also look at the entire value chain. So if we have a machine like this size, and then we have a unit like this, and if we can reduce the size to half the weight, and there is a motor driving this unit in the half the weight, a motor needed for the big component might be bigger than a motor needed for the smaller component. And so you are also enhancing the whole product system, not just the component what you are making with additive manufacturing. And that is something what companies will have to also then consider in their decisions. AM reduces the energy, the material, and also the emissions, and then the overall cost. So those are the cost drivers in every manufacturing or industrial sector. So this is an overview of the different the different life cycle phases. Sorry. So there is when we have a product, we have the design, and that is where you can mostly do a lot of the optimization with AM, and then you build the part physically on the AM machine. Then you use it, and then you come to the end of life. So there is what I'm calling the R's, 6 R's. So you should be able to ensure that your design is able to fulfill a lot of these 6 R's, if not all, to be able to ensure sustainable or circular economy. And AM is offering companies the means to rethink, redesign, and then reimagine designs that were not possible from previous manufacturing era. In conclusion, I would say that additive manufacturing is considered mostly from industrial companies, just like every other manufacturing company or any manufacturing method, from the enablers and then those who are not helping the company to grow. If you look at the pluses, the enablers, it gives lighter weight, and then it's also able to cause the engineers or the companies to create customized components. So for example, if somebody has had an accident and we need to replace a part of their body, we don't need to pick up anything, but we can actually measure your components or your parts and then really model it to suit your body so that the body can grow again through it. It's compatible with you, as an example. It also enhances functions, and that is also one of the things that is helping additive manufacturing to grow. Then there are things that are not helping it to grow or barriers to the adoption, such as the high investment starting costs, and then also post-processing. As I said, it's something that is really limiting the usage of metal-based additive manufacturing, especially laser powder bed fusion. In conclusion, again, I will say that additive manufacturing must be used with optimized components and simplified support structures. The support structures are needed to make sure the component builds well, but that notwithstanding, it must be considered well in advance because the complexity of them will affect the overall cost, and this is something that must be planned already on the computer or in advance. We must design to improve value creation through prolonging the life of the products, and not just because we've heard about additive manufacturing, we want to apply it, but there must be reasons such as to enhance the functionality, the lifetime or the service life. The manufacturing must be planned to reduce defects and the number of production runs. So we have the computers to run the simulation and see how well the parts operate, and this is something that we need to plan well in advance. We must design to improve life cycle costs. So looking at the design, manufacturing, the use, and then the end of life. All of these must be considered and not just the production only. Some recommendations for further studies is that companies or anybody hoping to use life cycle additive manufacturing or laser powder bed fusion for metals must consider the design process alternatives based on life cycle driven tools. It will help them find the best adoption plan. And also investigate effects of other process parameters. So new studies or people who want to further study must concentrate on helping out to find information about how the process parameters really affect the process. Because there are studies required to study the effect of the other. There are several of the processing parameters that affect the process, and this study only limited to five to six. So it is necessary that other studies are able to go deeper into it. The social aspects are not very much studied, and that is something that future studies can also study more on to see how it's affecting the social aspects. And then one thing that hindered also the additive manufacturing was lack of standards. And now there are standards coming up, but the companies are not using them. Or students are not using it. They still use the unstandard names, like some use 3D printing, for instance, in academic journals, or they use SLS, which is also an old term for the whole process. This is something that must also be enhanced, that when future studies are coming, they must use the terminologies as used by the official bodies to enhance the credibility of their work. Thank you very much, and here are some references for the study. Thank you very much. Kiitos paljon. Tack så mycket. Medasipa. Danke schön. Danke schön.
And once again, maturity of this process is pretty different. So meaning, of course, making this process more industrially implemented and sustainable, there is a strong drive not just for process development, but for process development together with material. When it comes to process itself, what was mentioned by Dr. Candidate, one of the most, I would say, negative part of EM is long build time, meaning the energy consumption increase simply because processes are pretty small. So once again, going back to the material and process combination, as you can see on this example that is now in the industrial manufacturing, you can significantly cut down the manufacturing time and therefore make a component that was from one side not interesting from the cost point of view, but also not sustainable because from the energy perspective, suddenly becomes very sustainable and very cost effective. So once again, going deep into the material and process understanding and integration with the proper design for EM. And here, all the tools we are talking about, simulation and proper design approach, are extremely important. Another important aspect of EM is, of course, supply chain. If you look on conventional EM, you have a long supply chain where you have manufacturing located pretty far from the customer. Then, of course, you have a lot of logistics, a lot of middlemen, and transportation costs, as well as CO2 footprint, where in case of additive manufacturing, you can really have manufacturing close to the customer and also integrate mass customization in place. But there is also another important perspective to take into account is manufacturing paradigm shift we are talking today, where we are moving from the mass production and mass customization to the personalization. And this personalization is also very much supported by additive manufacturing. So if you look on AM and you look at this mass individualization paradigm, additive manufacturing could be the revolutionary element that allows this type of implementation. But will it really be technologies will kick out all the technologies and we'll have only additive in 10, 20, 50 years? That's something I would really like to hear from doctoral candidate based on the work performed. But what we can see until now, I mean, if you look on AM, on the speed, on the cost, we always see what kind of machine should be machined, simply because it becomes faster, cheaper, and have lower environmental impact. Unless you have other incentives that make this component more interesting, make it more useful, beautiful, unique, reduce cost. This is something we know, but there is one very important aspect that is coming from all of the discussions we have overall. Also, there is a very big push from society. It's about sustainability. And this is something I think the doctoral candidates faced very well. It's one of the first work in this field, and therefore I will be very happy to discuss. Thank you very much. And to the doctoral candidate, should I share my presentation or?
Yes, please.
So first of all, I would like to thank once again doctoral candidate for an excellent presentation that clarified a lot of questions and made a very good introduction to our discussion. I really enjoy reading the thesis, and I would like to just go a bit deeper into the discussion. I also really like how doctoral candidate integrated results of the research paper in the kappa, in the introduction. Therefore, I would like just to go through mostly through the kappa and have some general questions about the papers. So, I would like to
Thank you for the question. When I moved to Finland, one of the things I saw from the beginning was how the environment was being catered for. And so I got more attracted to sustainability or circular economy issues. And then when I came to Lappeenranta University was when I first heard about additive manufacturing. It was very interesting to me, and then I tried to think what are some of the benefits of the process in relation to sustainability. And then I saw the gap. So I took the gap I saw to build on it to this end. Thank you.
Thank you very much. I think you have very good motivation. What are the main challenges you faced during the study?
Lack of data. There weren't enough, or there weren't suitable already existing studies where I could build upon. Most of the sustainability studies that were relating to additive manufacturing at the time of start were mainly judged or discussed from the polymeric plastics, in that sense, material aspect. So getting data was quite difficult, but luckily, as the study progressed, new studies were coming up and it was adding to what I had already studied. But time by time, that challenge was being overcome, or it's still getting overcome.
I think you list very, very important issue here is lack of the data, and that's something I think we will have to also discuss later on. But if you can just shortly mention which type of data you think are the ones missing, and what is the reason behind?
So additive manufacturing is very new, and let's say when we talk about the atomization phase where we are making the powder, this is an aspect is very, very secretive, or at the time when I started it was very secretive. So you couldn't get information about, let's say, energy consumption on the atomization phase, or companies were not willing to tell how their process are being done. They just sell the machine and they want you to buy the powder from them. So when you try to perform a study that you need this kind of information, it wasn't easy, and there weren't any literature you could actually get them from. So it was mostly dependent on what we had available at the time in the lab.
Yes, that's one of the very important points. Also, you mentioned it's very new technology. Did you get a feeling when asking companies to share data, it was a bit overprotective simply because it's new technology, and therefore understanding how to share the data and what data is sensitive is still not really well established?
Well, I think that we as human beings sometimes feel that when we have something, we need to get the best out of it. And I believe these companies at the time, now I think things are a bit open, so I'm talking about when I started, thought it was their way to really get it going and be the leaders. So, and it wasn't so clear what it was, and so people were being protective in that sense, I would say. And as more people come into it, and as standardization bodies come in, they kind of now have the rules guiding them, protection for their work also, so they are able to release, because at least now they have some sort of protection also for their work, what is coming out.
Thank you. What would you say are some of the factors to overcome to reach resource?
So, high energy consumption is one thing that we need to still work on to overcome the inefficiencies in additive laser powder bed fusion. Also, the limitation of materials. So, as you said in your presentation, that there are roughly about 32 or 30 something number of materials that can be used with additive manufacturing. This is something that needs to really be overcome. New materials have to really research has to really find new materials in such a way that the process will be applicable to wider materials and also expand its application. Another thing that will enhance the sustainability or the resource efficiency is the manufacturing time. So if the manufacturing time is too high or too long, it increases energy. So let's say the double lasers are able to reduce the time, and this is something that is coming up. More research is needed to enhance it. And also there is what we call the adaptive measures. So currently, the laser powder bed fusion is able to sense when there is a problem in production and stop it. It stops it and nothing is being done. But if there are this kind of adaptive loop system, it will be able to give command to the machine what kind of change or what kind of thing has to be done to sort of continue process without just stopping the process. It's good to have it stop, but enhancing the continuity of the process would then enhance better effectiveness. I would say these are some of the limitations or things to overcome to enhance resource inefficiency. Thank you.
Excellent answer. Thank you very much. And you mentioned two very important aspects of that. Of course, energy consumption. You mentioned double lasers. You know there are systems with 4 lasers, even now coming some with 8 and even 16. So do you think it's all increasing number of lasers, or do you think there are also other aspects that could improve manufacturing and energy consumption that way, of course?
Well, I would say that the component design, so additive manufacturing is best used when you have an optimized design. In that, if we want to make this, the function is to have it move. We don't need all this solid body. So for instance, having a component that will have the lattices, what I showed, or the topology optimization with the holes, will enhance material usage. You reduce the amount of material and also then reduce the building time. And by so doing, you kind of enhance the inefficiency with the process. Thank you.
Excellent. That's exactly what you're talking about. We build volume, and the less volume you build, the faster you build, meaning that you increase productivity by proper design. But what about other parameters, like, for example, increasing layer thickness, increasing gas, increasing scaling speed, and so on? Do you think we are really on the limits of manufacturability? Our processes we have are the ones we should have, or we should move to large manufacturing processes. Just for you, what I mean, additive manufacturing nowadays was very much driven by the high-end applications. Having 100% defect-free material for aerospace, where you don't have any, you can't forgive any small defects in any part of the volume. But as you show in your review from reports, AM has much broader application, automotive, consumer market, and so on. And that would allow us a bit higher tolerance to defect presence, as we have in other manufacturing methods. We have a lot of pores in casting, we use a lot of casting. We have a lot of defects in machine component, but we use a lot of machine components. So do you think we still have a space to push again to higher manufacturing for other markets than you?
Well, I would say that yes and no, because as you have said, people shouldn't just use additive manufacturing just for using. You should look at the use case, and I think that additive manufacturing is limitless in terms of the field it can be applied. So why not, if an industry feels that the benefits offered by additive manufacturing will suit and aim to their performance, definitely they should. And I think, yes, there is a future for more expansion to different fields of application.
Thank you very much. Excellent answer. Would you say that metal feedback is the future of manufacturing of metal components?
manufacturing, in my opinion, isn't the future per se, but it's a leading way to the future of optimized, better functioning, customized, lightweight components in applications where these functions are necessary. One thing I would like to say is that additive manufacturing can't replace traditional manufacturing entirely, because currently there is limitation of the size what can be built, and even if the size would be bigger, the surface quality of the component, if it requires some sort of smoothness or function, appearance, it's not suitable yet. So we still apply conventional manufacturing as part of additive manufacturing. So for me, I think it might replace some aspects, but not entirely the future of metal components. Thank you.
Thank you very much. I totally agree. Please, let's move on. And I was just wondering, now after you did some of your work, why you choose exactly laser powder fusion? Why not EBM? Why not binder jet? What was the main driving force to select one of these metal ion?
So as I said, laser powder bed fusion helps to achieve some components that are not possible with other metal-based additive manufacturing. And laser is a sustainable or green, how do we call it, green energy source. So it is also then not emitting any pollutions, or it doesn't have any sort of pollutants coming out to the environment. And because it can sort of really create functional components with the required, to the required reliability, and because also the high energy consumptions reported or seen were mostly reported from laser powder bed fusion. That was why I chose laser powder bed fusion. Thank you.
Thank you very much. Only one stuff, I was wondering, if you look on energy conversion, I just saw that, converting electrical energy into electron energy, so the electron beam can be a bit more efficient. But there is one aspect of it, as we mentioned, it's a high temperature process. Means that if you look on total energy consumption, you have to look actually how does the process in general with the whole AM manufacturing look. And that moves me to the next question that I get very often. What about LCC-driven AM technology selection? What you always very often guess, it comes, okay, if you look on these 4 technologies, which one should we select for our component? To produce the best component, but also to have it more sustainable. So my question is, do you think LPBF is the most sustainable or not? I'm sure we do not even probably have enough data to say that. What do you think, what are the steps to have LCC-driven tool for technology selection?
I would say that the model I have created is a first step that can be mirrored to other fields of AM technology. Companies will have to, or users will have to look at it and find the areas that interact or intertwine with their process and modify it to suit their application. I mean, every product design goes through the same sort of chain. So I think that this tool is quite suitable as a stepping tool for other application. Thank you.
Yes, I totally agree with your answer, because it's still the most mature technology, meaning you have all of the design or design tools are still developed, post-processing, so it's you have more data to evaluate it. But I think model as it is could be applied to other technologies as well, whenever they are fitted with the proper data. So I'm really looking forward to that. Thanks. So now if you look back on what you said, what do you think, what are the main issues potential users of VM have to consider to enhance cost effectiveness?
Thank you. So, I mentioned what is process parameters. And the process parameters are the influences or the aspects of the process that can affect the buildability. When I say buildability, how well the metals will interact with the laser source. So I would say that laser powder bed fusion is just a micro scale welding. If you know what welding is, just imagine it that way. So companies or users of additive manufacturing must be able to ensure that the process parameters they are using or what aspects they are using for their manufacturing ensures that there is sufficient interaction between the laser source and the material to form the needed melt. Too much heat, putting in too much heat might end up causing a deep hole, and a deep hole is just an empty hole, and this kind of hole can either cut through or vaporize the material. So when you have optimized the process parameters, you can be very sure that you have sufficient enough melting to form the required scan without actually causing harm to or losing what you aim to achieve. Also, there is what we call the spatters. So the spatters are like flying of the material, and this can cause bailing or balling on the component, and that can affect the surface quality of the component. And these all must be so creating the parts with high speed, the scanning speed. The scanning speed is the movement of the laser. So if you move it too fast, it might not melt, and if you move it too slow, it might also not melt. So there must be a balance, and these are things which are technical. So these are things that users must consider to be able to effectively use the process to overcome some of the cost advantages or to achieve cost effectiveness. And also, I think that companies must also look at if they really have to invest in the process, or they should use the service of a service provider. Sometimes you don't really have to make the parts. There are companies that are taking your product and they can print it for you. And it'll be more cost effective to use such an approach than to get the whole machine, because it's quite expensive. Thank you.
Thank you very much. You were talking a lot about process, but what do you think? Who is the one who should develop the process? Is it the customer? Is it technology provider? Is it a powder provider? You know, it's very, I would say, very hot and discussed questions. Who is the one responsible that this laser scan is good enough and create a property that customer is happy with?
So I think that, in my opinion, the machine providers are the ones building the machine, but the scientists are the ones to make the studies to find the optimal, what best will work for. And I think every company has this kind of research group going on. But when the industries are combining with research from the universities, they will kind of get mixed ideas and create best optimized systems for application. One thing I would say is that the process parameters, there are two of them, like in a machine kind of. Ones that are fixed, you can't do anything about them, and ones that you have flexibility. But usually the ones that are fixed by the companies are the most optimized to build the components. You can play around it with the other option, but like I said, there must be some sort of integration from both parties or all parties concerned. The customers must communicate what they need to the companies. Companies must engage them, and also the institutions that are engaged in additive manufacturing. So there should be some kind of ecosystem of all parties to be able to get a better system for the development of the process, and as well the standard bodies. Yeah, thank you.
Thank you. I think I can go for next slide, because it's exactly mentioned what you mentioned before. It's LCC-driven process optimization. So this is just one of the ways to do that. As you mentioned, there are multiply lasers, there are layer sequences, there are holders with gas flow, this can be gas type also. But questions there are at least two aspects of this as well. First of all, what are the boundary conditions? How do we know that now, if we put definitely this 80 micron layer thickness, as in this case, we cut the time four times, so from 400 hours to 100 hours, yeah? But as you mentioned before, we will compromise the surfaces. Then you have to look on post-EM in a different way, yeah? So what I mean here, if you look on the model you develop, and design for EM phase, typically take into account the whole EM process. So how do you put the boundary conditions on the process optimization?
So I would say that, from the example what you have down there, process parameters with the layer thickness of 20 micrometer and then the 80 micrometer. The 20 is having 458 hours, and then the 80 is having 111, then it says the optimized will be 246. So I would say that the boundary condition can be defined, or you can actually check this from the CAD model, sort of, and also the application of what you are going to use the component for. So if the component does not require some sort of micro layer build, then definitely you can think about the optimized option to use. And then also, if your application requires some specific layer thickness, then I guess you cannot go beyond, you can play around it. That would be my wide guess.
No, it's a very proper guess. So just to understand what this optimized means here. So in this component, it was built with different layer height, thicknesses, just because in the places you need a very high surface roughness, surface finish, you go for the process with high surface finish. And when you do not have high surface finish, you do a machining, because very often, as you mentioned, you do machining with a component, you can do with a higher build rate. So it's really the use case that put a limitation, but also not just a use case, but also a potential possibility to apply post-EM treatment, where we can reach it, like for example, there are cooling channels that are very complicated here, how it will compromise them, for example, can they be clean and so on. So I think the approach of LTC-driven process optimization is also a very important part of LTC-OPM in general, when, where, and how we move. So, thank you. So let's look on this nice table. What I really like about your thesis is very nice, elaborated tables where you put all information in a very social way. First I thought, we can go through some of your some of your comments, but I think going through some of your figures would be good. So if you look on this figure, you summarize your work, your objectives, and your research questions, and provide connection between them. I would say in a very excellent manner. But I thought now we have a bit more time. If you could and summarize factors affecting sustainability and circular economy of LPBF based on your study. How do you see it now? You started some years ago that looked pretty different. You did a very good way in that, you did a pretty good development over the time. So how do you see these factors now?
Thank you. Yes, so the factors that during this study I have realized are affecting the sustainability aspect of, the sustainability aspect and the circular economy of additive manufacturing, or maybe any other manufacturing method, will be the energy utilization, how well you utilize energy, the material consumption, or how well you use the materials, and then also how much waste you are creating or emissions you are creating. And then some of the aspects of additive manufacturing that can be used to enhance this sort of sustainability aspects, mainly the hotspots, were then the digitalization, as I said. So because there is digital tools, we can sort of run simulations based on FEM analysis or then CFA analysis, fluid dynamics, and kind of see how well this process will build out before we kind of really do the physical printing. And then also the hardware solution. So every machine system provider has different hardwares, and before using the additive manufacturing or before selecting, like I said, you don't just have to buy the machine, because you might buy the machine only to find out that it doesn't work or it doesn't suit your need, and it's quite expensive. So you need to sort of have the feasibility studies and check which hardware works best for your needs or your company products. And also the design system optimization is something that can really enhance the circular sustainability. You know, I said that circularity is also extending the product life. So if we are able to design optimized components that will enhance the lifetime of components or products, then we are able to enhance the circularity of these components. Also about the process parameter optimization, if we are able to have well optimized products, there will be less faulty builds and the need to repeat a build phase, and reducing that will then also help to enhance the sustainability aspect, because if you have a failed part, you are wasting energy, you are wasting material, but the lesser you reduce such waste, you will be enhancing the sustainability aspect. And also, there is the need to consider the post-use phase. So we shouldn't design for one use, but we should design such that, for instance, let me use this pen as an example. This is an additive manufactured pen. It's just like our regular pen, what we have, right? So you see that it's easy. When the pen is finished, you can just sort of, so this pen will have, it can be reused and reused and reused. And also, it could also be designed such that it has double functionality. This edge could be designed so that something else is coming here as a function. Normally, normal pen, we just have the lid, plastic. Or even if it's pen, now, okay, we have the touch screen, but let's talk about the engineering aspect. This can be designed so that it's a screw, and then you have a pen and a screw. So in that sense, we are also then reducing the amount of production. Instead of making screws separately, we can make screw and a pen. And at the end of the day, we still need the middle that we can hold. So if the pen can serve the two, why not? And these are some of the ways what I think will enhance the sustainability aspects of and the circularity of additive manufacturing.
Excellent. Very, 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 very good answer. As technologies, and then trying to find a way to remanufacture and to repair. Now we are in a new paradigm of additive manufacturing. Probably can design our component for them with the idea that we can remanufacture and repair them. Meaning that we can introduce the initial design, making our life much easier because you have your design ready. It's just to adjust it for improving repair partly.
Okay, thank you. So there is what we call DED, Directed Energy Deposition, and it's a type of additive manufacturing that we are coating surfaces to enhance their usability even when they are broken parts or if they are worn out. Now let's look at what is reverse engineering. So let's say that I keep using this because that's what I'm gonna have. Let's say that I have this, it's old-fashioned part. I want to redesign it. We are, let's say, a car manufacturer. We need the parts, but it's out of stock. We don't have it. And you know, traditional manufacturing usually needs a mold. It usually needs some fixtures. And investing in those can be very expensive, and maybe we need just one. Instead of getting the mold and the fixtures with additive manufacturing, we can scan the old parts, what is broken. Even when we don't have the available data, we can scan it to get the CAD model, make some corrections based on computer data, and then we start the steps I showed of additive manufacturing. So from there, we can rebuild the parts with additive manufacturing. to replace the broken part, so we don't need to throw the part away. When I'm saying this, you might not see it as important, but if you are in really high-end industrial sector, you will see the benefit. Because if an airplane has to fly and something is broken, and every time the airplane is on the land, it loses lots of money. But if instead of waiting to get the mold and all the long processes, they have a system where they can just maneuver things through the computer and then print it with AM, you will see the benefit, because it really saves a lot of time, also cost, and also the downtime on the ground can be saved or reduced drastically. So also with additive manufacturing, we can be sure that when components are made, they are possible to be reused. And then in that case, we are talking about enhancing the remanufacturing aspect of industries. Yeah.
Exactly. So I think what I meant was what you described, but you can also do it well. Yeah. So for example, if you take your pen you just discussed, yes, and you have a varied component on it, you can cut it, and if you can satisfy that you have a plane, you can build on top with LPBF. This is done in the molding industry. They do repair in the same way. And as you mentioned about functional components for airplanes, I mean, there is also not all the components are in function. There's always functional surfaces that are varying, meaning they can be, if properly designed, they can be cut and repaired. This is also a very important aspect of design for it. This is something we already touched upon. If you look on your table, what about the input? And we talk about this input number of times, but I would like you to hear, top three. No, I mean, you mentioned that there is always an issue to get the proper input, proper quantitative data, yeah? Utilization, energy consumption by single laser, how system will change it, you change it to the multi-laser. So what do you think as a top, what is the most important input values you would like to get? If you can take three the most relevant.
Well, I would say the material, what we are putting into the process. When the material is not suitable enough, the process will fail. Also, the design we are building, we must be able to be sure that the design is printable, and the design will be able to. So, if you look at DFAM, it's like a guide. It gives a guideline of what can be printed and what cannot be printed, and what are the features we need to use to make sure that the part prints well. So these are things I would say that are important to look at, and also I would say that the heat input is something that's, or the energy that is going into it is something that we need to also check, so that the process will be well or be effectively built. And for me, I think this will be the most affecting things to look at in additive manufacturing, especially the metal, and definitely the post-processing, and that comes from the complexity of the support structures. So I think it's all about DFAM also, because the support structures can very much bring surprises, which you might not expect.
Exactly. And I think that's very important always to remember. DFAM includes everything. And that's why it is so complex. It's not just design. It is really designed for the whole chain, where design is the initial part. Excellent. You don't have to read all of this question, but when I start teaching additive 3 years ago, and that time everyone was talking that LPBF will grow because now we can put 2 lasers, 4 lasers, 16 lasers, and increase powder bed, meter by meter, 2 meters by 2 meters, and so on. So that's what I really strongly believed and put into my students' hands 4 years ago. Now the students working in industry come back to me and say, yeah, but it didn't move that way. Now what you see is this build plates actually become smaller in order to make processes more robust. So my question here is, AM is still, and LPBF in general, it's still not a mature technology. So what do you think where, if you look on your understanding, your evaluation of technology, where it will move, and what would be the aspect, LCC aspect affecting design for EM, for this technology?
Well, I will assume that the atomization phase, the powder phase, it's something that still needs a lot of studies or a lot of information to help consider the whole life cycle cost, because currently there aren't really what sort of energy consumptions are on the powder phase. We don't have this, or even if there is, at least I was not fortunate enough to find such. So that is something that I think that it could be included in the life cycle model, because then we have the very whole new, whole broad value chain of the metal-based additive manufacturing. So that is one thing I would definitely suggest, or think that is still missing and would be necessary to sort of, and also to have it a specific case, so you cannot generalize it. As you see, the model shows weight reduction in the use phase.
So how do you see maturity of the tool or easiness of build play or build volume utilization when it comes to EM? Or do you see it irrelevant?
I'm not quite sure if I got that question right.
So just imagine, I mean, you have very limited build volume, yeah?
Build volume?
Yes, volume where you build your component. Yeah?
Okay.
So you design your pen, we like to talk about pen today. You know? You can design them to build them vertically, one after another. You can put a lot of them. It's going to be not looking very nice.
Okay.
If
you
design
mean
it.
plastic?
And of course, you can incline it, and you will have much less pens built, meaning that your process will be longer, your sustainability aspect goes down. And this is very important aspect that, as minimum, I see very often forgotten in design for EM. There is a very well dedicated work to design component to optimize it for EM. But then when it comes to orientation in the build volume, you can fit too low amount of components, meaning process will become pretty lengthy and not cost efficient, and in that way not sustainable at all, because it could be over optimized when it comes to support and so on. And so also where in the process, because it's a loop, you know, so then you have to go back and redesign a component. So how do you do this looping design for it?
So I will suppose this is, you are talking about platform utilization?
Yes.
Okay, all right, thanks. So the machine build plates, depending on the size, must always be utilized to the maximum. And luckily, what I saw last week at a fair in Finland, Tampere, Alihankita, was a design case from 3D Step, where they have a component and it was quite utilized platform. So the platform is such that, or the components were built, let's say ground. Usually we are talking about using the whole platform, yes. But now there's a further step of stacking components on each other. So then you are utilizing the base plate, but you're also utilizing the height. So if the component is not filling the whole height, the maximum height, you can still sort of build on top of it. And all of these are things you cannot go and do on the machine. You need to do them on the computer to see how well they will function, they will be able to build. So the support structures, when we are talking about support structures, if you don't get it or if it's a little bit confusing, it's just a base, because like Prof said, additive manufacturing laser powder bed fusion is building from nothing. It's just the board, the plate. So something must attach if I want to build this pen, and I build directly to the board. and I cut it, because when I finish I should cut it, I might end up cutting this part. So some material is created under it to combine or attach this part to the plate. That is one. Also, because laser powder bed fusion has a lot of input heat, these support structures are also conducting or taking heat away from this away, so that the part is not like collapsing or breaking. So there are other functions of the support structures are not just there, but they are performing several functions. So coming back to the question then is that the better you utilize the flat surface and also the height, the better usage of.
That's what we call the build volume utilization. So this is something that is done in EBM. This is where we're moving with LPBM. Okay, thank you. And last question here, topology optimization. Do you see that topology optimization can be directly applied to EM? Or do you have to do something else when you want to build a component? I mean, now you have this nice software doing these bionic designs. I have a lot of students coming with these fantastic designs that they want to print it by EM. So do you think it's directly applied, or should you do something else?
Thank you. As far as I have seen so far from literature and also from what I have done myself, if we look at the initial CAD model, let's say that is the model. Then if you come to the second model, which is optimized design, so that is the topology optimized design generated by the computer. But as you asked, the generated topology optimized components or design might not be suitable for additive manufacturing, because, like I said, the DFAM tells the guidelines of limitations of what can be printed and what cannot be printed, the angles that must be considered. And if you look at the third design, it is then telling about fine-tuning the design that the computer has given you to be able to be printed on additive manufacturing. If it's another manufacturing method, there might be limitations to also look at, but the directly given generated design of the topology might not be suitable. There is always some kind of, or there might be the need for post redesigning, manually manipulating to suit additive manufacturing, because the CAD model or the CAD system might not understand the DFAM rules, but you as the engineer will understand it better. You look at it and then you model it to suit additive manufacturing. And that is all about DFAM. Thank you.
Fantastic answer, and this is something we see very often. Topology optimization is not designed for EM. It's an input values, and you have to put the limitations of buildability. So there is a loop, very good. So I have, I think, too many slides prepared, so probably I have to go a bit faster. That's something you already covered. So I was just looking on this nice figure about E3, and can you describe, if you look on this figure, where LPBF in perspective of these three bottom-up approaches? What is the impact on sustainability from profit point of view, planet point of view?
So, laser powder bed fusion is helping to reduce the the material usage, and of course, if you use the best optimized process parameters, we can also enhance the energy use. Then it is creating jobs, it is creating new field of research in terms of social aspects, and it's also enhancing the well-being of people. If people get accidents and we can really create them the part what they need, it's not like pick anything, but we really build to suit their body. That is enhancing the social well-being of people. And then the economic aspects, I would say that the circular economy is one thing that really, I would say, covers the whole benefit of laser powder bed fusion to the sustainability. And then I want to believe that on page 93 of my thesis, page 93, big number materials, energy, it's enhancing the effectiveness. So we are saying that additive manufacturing is enhancing how well things are done to effectively satisfy functions, and also the efficacy of these components. It's all about using the right tools that will enhance these three aspects of efficiency, effectiveness, and efficacy. And then we can talk about additive manufacturing sustainability, sort of reaching that E3. Thank you, sir.
Thank you very much. So I will skip these ones. Now let's look on this diagram. I think here you put very well elaborated limitations of powder bed fusion. But what I was wondering, does these limitations have the same impact on different sectors? So for example, if you look on the aerospace as one sector, low buildings build probably will be not as bad because components are really high cost. But if you look on automotive industry where you need a high manufacturing rate, that is a very limiting parameter. So that's what I was wondering, if you look critically on this figure, can you just describe, can you emphasize, top three impacting the limitations of LPBF, and also how do you feel about them as it comes to different industrial sectors?
Okay, thank you. I think that the most affecting, firstly, will be the affecting parameters, because there are several of them and you might not easily identify which ones to best control or look at to ensure that the process goes well. Also, the need for the support structures can be very, very confusing and limiting. Regardless the application, we will need support structure, at least so according to the current state of the art. So that is something that is irrespective of the application. So whether automotive or aerospace, these affect it very much. And also the high, the cost of the metal and then the metal powder and the machine. I will combine those as one, even though they are separated in the diagram, because they also are irrespective of the application. Yes, thank you.
Very good. You go back a bit, material, you have this high metal powder cost. Do you think it's the same limiting factor for different technologies? If powder costs 100 euro, is it expensive? Is the same high cost for aerospace and automotive?
Maybe no, because let's take for instance titanium. There are things aerospace benefits most from with titanium. Titanium is very expensive material, but if the aerospace, for instance, can print titanium parts without any difficulty, as AM offers, then the cost of the material really doesn't play a role, because if they cannot traditionally manufacture titanium, which they really need, then the cost of the manufacturing would rather be more important than the cost of the material. So the price maybe doesn't, so to correct earlier or to make a change a little bit to what I said earlier, the cost of the material, definitely. Thank you for reminding me, I didn't think about that. The application does not really sort of, it depends on the benefit. Let me just say that this figure was or is based on the state of the art at the time of when this was done. For instance, if you look at the low build speed or the part quality per se, but in AM then we are talking about the powder, but the powder is also then the material.
Yes, exactly. Okay, thank you very much. Let's move because I see it taking a bit too much of time. Is it coming from clean energy sources, or it's energy you don't produce any emissions?
Yes, sir. As I said earlier, so laser source, laser energy, it's a laser source, but in an area where the electric grid or electrical power is generated from coal, then we can't talk about green energy in that sense. But in the process phase, the laser itself is quite emission free.
Excellent. That's exactly what I was asking about. There is, of course, also effect of the energy source itself. I have just a short question here. You say the possibility of reusing surplus powder. From sustainability point of view, is it a possibility, is it a must to reuse the powder? Otherwise, we have to throw a lot of material.
I am not quite aware what the industries are doing, but for research purposes, there are studies that are comparing how much we can reuse a powder before it becomes not usable again. Yes. So as you build, the laser is creating spatters. There are interactions. There are spatters flowing to mix with the excess powder. And so definitely reusing the powder is something that is possible, but as to whether the reusability will give the same function of the components is what needs further studies. And also mostly these powders, some people say you can sieve it, but I believe that others also are arguing that even if you sieve it, there will still be some particles that are unwanted. So it's case by case. If the reapplication requires very, very pure virgin powder, then maybe it might not be usable. But if it is something that is not of that much interest, then yes, powder reusability is something that is really a factor or benefits of additive manufacturing. We can use the powder, we can recondition it through some ways to bring the properties as it was before the building phase or the first time use. And definitely always it is mixed with virgin powder. So yeah.
Thanks. You know, I have a research group of around 12 PhD students, as minimum 1/3 of them looking exactly in this aspect of powder reusability. It's a very complex issue. And I would tell there are industries who reuse it and there are industries that does not. Why they do not do it? Simply because they do not know if it works or not. And that, of course, has a very strong impact on sustainability process. This is why I think it's very, very important question. Let's move on. I like this graph. It's come from Fraunhofer. I also used it a bit for teaching before. So do you really believe that the cost of the AM component is independent of the load size? Is it really constant? If you have one component or you have 100 components? It's really independent on the complexity of the component. Is it one, or is it simpler component? Is it very complicated component?
Thank you, sir. So I would say that, as we have said, or as I've said already, increasing the complexities of the support structure can bring surprise prices. And at that moment, it's no more constant. So optimize the support structure so that you can achieve close enough to this constant cost structure of additive manufacturing. Other than that, it could go as high as the CM is CM, meaning the conventional manufacturing is going, or close to it, or follow it somehow. And that is what I think that companies must really take care to look at this way. And also the lot size is not that constant, because if you utilize the platform, like you said, the volume enough, it will no more be constant. It could then be reducing, or if you don't use it wisely enough, then you but it's also about the other costs. If you are using a gas, shielding gas, the cost is anyway the same. If you are using energy to move the platform, the cost is anyway the same. The energy that will be used to move the platform will be the same if you are building 1, 2, 3, or if you are building 10. It's the same. So these are things that, to avoid the surprising or the hidden costs, companies might be aware of some of these, that it's not that straight. It can be more, it can be less, it can even be as high as the CM if not well optimized. Thank you.
Yes, so what I'm more into, so my interpretation of this is, if you look on lot size, as you mentioned, you will have a decrease because you can utilize more components. And when you look on design aspects, you will also have increasing costs, increasing design complexity, because you also have engineering costs, and you also have a cost of support. Meaning the more complex is your design, the more complex is your design engineering cost, but there's also more expensive support to move on. And I think what is also important is they're not going in line. You remember you have this very nice appendix where you do your fantastic designs. There are designs that are not reachable by conventional manufacturing. And I think this is where you have a sweet spot of additive manufacturing, where you have designs of such a complexity where conventional manufacturing will simply not make so much of a sense, and this way you can go for it. So now let's move to my favorite image of your thesis, my really favorite. I really like SWOT, because it can really identify in a fast and reliable way if what you are doing is the right way to do it. Looking on your component, and I think it also creates a bit of self-awareness, and also looking on your on critical thinking about it. So if you look on the strengths you identified, what I was wondering, it's about reduce the cycle time and downtime. What did you really mean there?
So when we talk about the cycle time, so I'm a customer, I come to company A and I need a component. Or I am a company, something has broken down, or we need a new design. From the time when we are starting to the end when we are ending, I could term it as the lead time or the cycle time in that sense. So the cycle time here is talking about then the lead time or the cycle time, the building phase. So with AM, as I said, it quite reduces because the long chain of weights are removed, because you can very much just digitally redesign or create new designs without having to really waste a lot of time. And then also the downtime, if there is a breakdown in application, you do not have to wait for a longer time. Within a very short time, you can build new parts to replace the parts, and then you are reducing the downtime of the operations. Okay, yeah, of operations. Yes, thank you.
Yeah, exactly. So what I thought were more about time to market, as we call it, yeah. From your initial request to actually final components, this is what you significantly PATRICIA. Yeah. You mentioned no special skills are required. I thought design for EM is pretty complicated. What do you really mean there?
Yes, so additive manufacturing itself has different aspects that people without knowledge can really go into. And DFAM is one aspect of additive manufacturing, which could or is complicated and needs some sort of detailed understanding of the process. So firstly, attracting the people to the process is quite easy. And I think that this SWOT is for AM, not laser powder bed fusion. And I think that AM, as I have said, is also the 3D printing. So somebody can just get the plastic printer, they want to print this, they don't need any skills, they can just sort of create their design and push the button and it's printing it. They don't sort of really have to do detailed engineering DFAM in that sense. So on the broader scope, it is accessible and easy without any skill. But if we are then going into industrial additive manufacturing, then definitely there is some kind of detailed engineering learning that one must acquire to be able to use it. Thank you, sir.
Thank you. I'll just put this last point on this graphic. We could discuss it for an hour, but unfortunately that's not the time we have. What about hybrid materials? This is an extremely interesting point that you lifted. What do you mean here about hybrid manufacturing? And what type of hybrid materials? So what do you see perspective of hybrid materials in general for you?
Yes, thank you, sir. So, when we talk about hybrid material, we are talking about building a material out of more than one material in that sense. So, additive manufacturing, as we said, is only limited to a number of materials. So, assuming that we want to build this product, and this product, we need it in an application that has to have some material properties, and AM cannot print that material, but yet we need the complexity that AM offers. Let's say the internal cooling channels that are better enhanced with additive manufacturing. We could print the parts, let's say from the base material, stainless steel, for example, which is quite a common material with AM, laser powder bed fusion. Then we will coat the surface with the functional material, what will be better in the application. So then we are combining the functionality or the benefit of the complex body, the internal complex flow channels that AM offers, and then we are coating the surface so that the product can function effectively without causing any sort of problems in the use phase. Then we are talking about this multi-material benefit with additive manufacturing. Because yes, if a part is printed, again in the just ended Mesut Fair last week, we saw again, I saw again a case of printed components that has been coated with paint to enhance the surface functionality. If we are using a component in a harsh environment, we might need to coat the surface to protect it from, let's say, rusting or any sort of thing that might happen to it. So in that case, we are able to sort of build from additive manufacturing for the functionality it offers, and then also coat it with another material for the functions of application. Thank you, sir.
Thank you very much. So I would, unfortunately, don't have the time to go through my papers. I have just one question here. If you look in your geometries you selected here, do you think they are the ones, especially looking into the graphs we are talking about, are they the ones really showing potential of them?
No, please.
And I think it's very important because yes, I mean they are not too complicated. Meaning that if you want to really show impact, and I think still it's extremely good cases. I think it's one of the very rare work where I saw comparison of SNC and AM in a good way. So I think you did a fantastic work here, and going one step more would be fantastic. But I would also like to mention another point. What about material type? If you look on iron-based, nickel-based aluminium, machining of these materials are very different. It's pretty easy to machine aluminium, it's also very cheap. When it comes to nickel-based support, it's much more expensive and difficult. So how do you feel, I mean, when you add material complexity of component and material time? And this is something that I think we often meet, when we disconnect design for EM and material.
Yeah. So, as you said, aluminium is quite easy to machine. Why machine it? Why use additive manufacturing if you can easily get it done with conventional manufacturing. And you are not looking for some function, some design geometry that conventional manufacturing cannot offer. If you are machining an aluminum with solid body, nothing really that additive manufacturing can do alone, then machine it. But if it's something that the aluminum is good, you can use some sort of design complexities with AM. Then using CM is not good enough. You must then think about, so it's about looking at the whole, not just the design, but the application also to decide whether it is suitable enough or not. And also, definitely, when it comes to the materials that are difficult to machine, why not AM if it will ease out the manufacturing process? Thank you, sir.
Exactly. I mean, if you're component one and if it's very difficult to machine nickel-based superalloys, you make probably sense even there, but for aluminium, probably not. I think I have to move through because I think from the audience keeping you for so long time, I would not sound nice. So I will move, I think, to the end of my presentation. And just to summarize everything we talked today, we had a really fantastic discussion. I would just like to hear now, after our discussion, if you could elaborate on hotspots, really elements to improve. And please select 3 top ones.
The design optimization, the hardware solutions, and the process affecting parameters.
Great. I'm very happy with that. So now let's move to some concluding questions. You went really a long way through this study. You saw a huge development of AM. Now just imagine, by some reason, you get into this time machine and it will push you back 5 or 7 years ago. What would you do different? Knowing what you know now. Probably nothing, I mean, that's I was just wondering.
There is something I could do. One thing would be to have more a design that really takes into an account the benefits of additive manufacture. As you asked, my samples didn't quite show the benefits additive manufacturing offers. Another thing would have also been to really look at the dissimilar material possibility offered by additive manufacturing. These are some of the things that have come up recently, because when I started, AM keeps growing, like I said, day in, day out. There are new surprises. I think earlier you couldn't even print a copper, but last week I saw really like a copper heat exchanger printed, and it's functional. It's not just a prototype anymore, but functional components. So there are things I would have done differently, but definitely I can't list all of them.
Yeah, that's life. We have to have the best of it, and I think this is what you did. But now if you would have opportunity to add something, so you mentioned materials, but I'm not sure, would you like to add some measurement techniques? Like to get, I don't know, machine with a green laser. What would you think when it comes to the characterization manufacturing techniques that you think very important to include in such study? Powder atomization probably, I don't know. To buy a powder atomizer and do atomization and check how much energy it actually eats and what does it produce.
One thing I'm very curious about so far, and I haven't found an answer or a way to get it done or see, is the atomization phase of the powder. I really want to see what really goes on there and how much really additive manufacturing is supporting sustainability, because knowing that phase will really give the whole value chain sustainability study aspects. And that is something that I think is still very missing, and I would want to see that aspect.
Great. So now, today, in some minutes, you will become a doctor, and then you continue your research career. how would you plan this project? What will be the steps you will take? So you mentioned optimization. Is there something else you would like to include?
There is something I have realized out of this study, and it goes into the business aspects of companies, and that is the leanness additive manufacturing is offering. So we talk about lean manufacturing all the time, but is additive manufacturing really enhancing the leanness of manufacturing companies? And that is also something what I think, if I have the opportunity to further, I would want to also have a look at that aspect.
You know, in the ideal case scenario, tomorrow you get your PhD student. And then what you have to do is the same what Peter did with you. It's actually, Professor Peter did with you, is to put research questions. What would be 3 top research questions you will put for your PhD thesis, for your student?
It's the student's responsibility to find their research question. Before you want to do research, you should
That's
have
excellent.
questions
You
to
can,
work on.
and I just totally accept.
So I could guide them, but definitely I'm not going to give them research questions. Thank you, sir.
Okay, but I would say I'm really out of the time, and I'm really satisfied with the thesis. I would say it was really adequately examined. And if it's okay, with honored co-teachers, I would like to make a final statement. PhD thesis by Patricia Nyamekye entitled Life Cycle Cost-Driven Design for Additive Manufacturing, the Frontier to Sustainable Manufacturing in LPBF, is focusing on one of the hottest topics of metal additive manufacturing, namely sustainability of metal additive manufacturing in general, as well as biotechnology fusion in particular. At the current state of the art, metal AM in the stage of wider adoption by industry, as development of hardware during last 2 decades reached a point allowing robust AM of complex components in low and medium scales. There is a strong pull from a number of industrial sectors that are attracted to the almost unlimited design flexibility, as was shown today, and high material utilization by AM, and hence inherent sustainability of the AM technology. However, technology is very young, and there are limited knowledge on sustainability aspects of the metal AM. Hence, understanding sustainability aspects of AM in general, and LPBM in particular, are vital to reveal the strengths and weaknesses of the technology and determine potential of its expansion in other most cost-sensitive industrial sectors, as we also discussed today. Thesis covers environmental and economic aspect of sustainability of metal LPBF in excellent manner, and approach to a life cycle inventory and support chain analysis developed in thesis provide an excellent way for identification of the best adoption plan for LPBF and increase the value from idea generation through the proper implementation of metal EM to its end of life. Thesis illustrates that LCC-driven model is a useful tool to support decision approach are covered in the thesis, including business models, value chain analysis, and my favorite part, as I mentioned, SWOT analysis. The most significant contribution of the thesis is integrated LCC-driven design for AM model that shows a strong potential to be used as a decision-making tool for proper design, and hence successful adoption of metal AM for a variety of components in different industrial sectors, considering necessary performance, resource, energy, and cost efficiency, as well as minimum environmental impact. Research methodology used is well thought through and elaborated in detail in order to relate sustainability from energy consumption, raw material usage, need of transportation, and waste creation, compared to CNC machine, life cycle inventory, and supply chain analysis were applied, considering advantages and limitations of both technologies. Even impact of powder, feedstock, and post-EM was covered in general terms due to the lack of data. However, it was very nicely covered during our discussion. Energy of LPBF fabrication, input raw material, useful outputs raised in the emissions were studied using LCA tool. Review and case studies were used to study effect of simulation-driven, designed for EM on the life cycle cost. Hence, it can be concluded that research methods used in the thesis were appropriate and elaborated to require depth to cover research topic to the extent possible, considering available time and resources. Excellent scientific contribution by doctoral candidate is confirmed by 5 journal papers published in renowned scientific journals. Thesis is well written, providing detailed introduction to the topic, method, description, as well as summary of results. Hence, I found PhD thesis well written and covering the research topic in excellent manner. I also find scientific contribution by doctoral candidate to the field of sustainability of metal EM as excellent, containing strong evidence of creativity and innovation capacity. Doctoral candidate could also clearly demonstrate her ability to defend her work at the public examination in excellent manner. And with this, I would like to congratulate.
It's time to help me welcome Travis Green, everybody. You've done so much for me, I cannot tell it all.